Example 4. Some students are collecting data on a model rocket launch. They use video analysis software to record the height and time of the rocket at various points. Unfortunately, their camera is aimed wrong and the rocket goes above the viewing frame of the camera. Here are the data they collected. So, this is our data, and if we graph it and look at it, it appears to be quadratic. And if we think about it, it's the position of a falling object, so it should be quadratic because we shoot a rocket, it goes up, it comes down, it's quadratic. So we can see some evidence of that here, although with the missing data, we can't be sure. In the scatter diagram itself, we see a strong positive association in the first part and a strong negative in the second. So here it looks like it's going up, here it looks like it's going down, but we don't know what's going on up there, okay? But there's evidence of a nonlinear relationship because it's not doing the same thing on both sides, okay? If it were linear, it would be strong positive the whole way or strong negative the whole way. It wouldn't switch midway like this one does. So, for part B, they tell us the falling object model is given as S sub t is 1/2 at squared plus v sub 0 t plus s sub 0, where s sub t is the position at time t, a is total acceleration due to gravity, v sub 0 is the initial velocity, and s sub 0 is the initial position. Use your graphing calculator to find the best fit values of a, v0, and s. So we're told to use the calculator and do a quadratic model. So in the calculator, we put our data in L1 and L2. Then we tell our calculator to do the quadratic regression. So if we do a quadratic regression, we can tell our calculator to store these values. So if we tell the calculator to store the values, it's going to graph everything at once. So I'm going to make a separate video with the calculator steps to get the quadratic regression and the scatter plot all there together. So I'll put that separately in case you need to review that. I think it's better than putting it in the lesson with everything else. So from the calculator, the quadratic regression gives us this value. So it tells us that our s of t is equal to negative 4.65 t squared plus 46.4 t plus 0.687 with a coefficient of determination of r squared equals 0.996. So that means 1/2 a is equal to negative 4.65, but we want a, so we have to double that. So that's where we have to be careful because we want to find a. So this is a 1/2 a because based on the model, it's a 1/2 of a, so we have to double it. The other two, v sub 0 and s sub 0, we can just pull straight out of the model. Interpret the values of v sub 0 and s sub 0 in context. So v sub 0 is the initial velocity when the rocket is launched is 46.4 meters per second. The initial position is 0.687 meters, so that could be the height of the launch pad. So, however, our data indicates that the height of the rocket at time t equals 0 is 0, so there must be error present in the data collection or the model. So, this is where, if we look at it back up here, remember our r squared value was 0.996. So it's very close, but not exactly equal to 1. So it's not perfect, but it's still very good. So there's a slight amount of error, and it could be based on the model, or it could be based on the data collection. We don't know which one. Because if we look, our time and height are modeled as 0, 0. On Earth, at sea level, acceleration due to gravity is the constant g equals negative 9.81 meters per second squared. Compare to the value of a and interpret the difference. So the value we got from the model was negative 9.3 meters per second squared. So this is less than the gravitational constant. So the gravitational constant only describes the rate of acceleration if no other forces are present. In this case, we can assume air resistance is acting against the model rocket and causing its net acceleration to be less than g. So in a vacuum, your gravitational pull would be that. But because we have some wind resistance, our gravitational pull ends up being a little bit smaller. So its net acceleration is a little bit less than what gravity would be due to air resistance. Interpret the coefficient of determination for the model. So if we remember, the coefficient of determination was r squared equals 0.996. So that indicates that the quadratic model accounts for 99.6% of the variation in height using time as the explanatory variable. So use your model to predict the maximum height of the model rocket and the time at which this occurred. So remember, that was the part of our data that we did not get to record. Remember, it was off the chart here. We couldn't record it. There was a mistake. So we take our equation. So remember, the maximum happens at the vertex. And to find the x-coordinate, or in this case, the t-coordinate of the vertex, it's negative b over 2a. So that's what we started with here, the opposite of b over 2 times a, which gave us 4.97 seconds. So that's when the maximum height happens, but to figure out how high it is, we have to substitute that into the model that we're given, which gives us a height of 116 meters. So the maximum height of 116 meters occurred at 4.97 seconds. So in this example, we're going to do a throwback to trigonometry. So the table below shows water temperature at a buoy in the Gulf of Mexico on several days of the year. Use the sine regression function in your graphing calculator to find a model for the temperature of the water. So remember, we're using L1, L2, and then sine reg. And then this is what you're given. And then use your model to estimate the temperature on the 90th day of the year. So then we just take 90, substitute it in for T, and you should get out 71.4 degrees. I encourage you to do this on your own in your calculator and compare your answers to what we got. Also, it's important to notice that a sine regression does not give an r squared value. So if you're trying to determine if a sine regression is good, you can't look at the coefficient of determination because your calculator does not calculate that. So instead, you have to look at the fit of the points. In this lesson, we reviewed how to find different types of models using your graphing calculator. Like I said earlier, I'm going to make a separate video of the calculator steps in case you need them, and I'm going to show you how to make sure that your diagnostics are turned on so you can get that Pearson's correlation coefficient, and you can also get the coefficient of determination to show up. And also I'm going to show you how to put the model in so you can get your scatter plot at the same time as your model. So if you need help with any of that, be sure to look out for that other video.